We're going to continue our discussion of oscillations and waves by looking again at wave packets. So, first of all, let's recap what we know about wave pulses. Remember we said that wave pulses were localized non-periodic disturbances propagating through a material. So we introduced these as being the elements of starting to think about a wave. We also said these could take the form of any function where the localized disturbance y is a function of x, the direction in the propagation, and we also said this is known as a wave packet. As we went through our discussion of waves, we found that we could express a wave pulse as a sum of harmonic waves of different frequencies. This was our idea of a Fourier transform, so thinking about expressing this localized wave pulse as a series of harmonic waves. And if we have a non-periodic disturbance, that means we use an infinite array of frequencies to create that wave packet. Okay, so we said that if a phase velocity is common to all frequencies, that means every frequency within that wave packet moves at the same velocity. That means that the pulse doesn't change shape. And we call this a non-dispersive medium. However, the phase velocity applies to each individual frequency within that wave packet. These all add together to give us the group velocity, the velocity of the packet as a whole. If we're working in non-dispersive media, then that group velocity is equal to the phase velocity. And we can think of that group velocity as the rate at which energy is carried through the material. Okay, so this is all an idealized case working in non-dispersive media, but what happens when we look at dispersive media? Fundamentally, in a dispersive medium, the phase velocity depends on the frequency of the wave. And the end result of that is that the wave packet spreads out over distance. So as the distance increases, higher frequencies travel faster, lower frequencies travel slower, and the wave pulse spreads out. So in this particular animation, we've shown that the phase velocity increases with frequency. There are two main demonstrations of this that we'll be familiar with in our experience. The first of which is the dispersion of light as it passes through dispersive media, and the second is the dispersion of sound as it passes through dispersive media. I'm going to deal with each of these in turn. We're broadly familiar with the concept of light dispersing in optical media, so higher frequencies travelling faster in dispersive media than lower frequencies, and we're most familiar with this in terms of the separation of light into component parts. The refractive index of light is based on the speed of light in that medium. We'll talk more about that later, but the fundamental take-home result is that higher frequencies look as though they are bent more as they pass through this prism that we've shown here, and this separates a white wave packet into its different frequencies. We'll talk more about this later on. Sound also experiences the same phenomenon in solid media. We find higher frequencies travel faster in the dispersive medium than lower frequencies do, and we can introduce a wave packet by an impact, so hitting a material with a hammer. In the material, higher frequencies travel faster, so as we stand further from the source of the sound, the effect is more pronounced. We readily observe this on railway platforms. We often hear a pinging sound as the train approaches because those high frequencies travel through the rail considerably faster than any sound through the air or the lower frequencies from the train approaching the platform. So we hear those higher frequencies first. This example here from the Instagram user Alex Colgan displays the cracking of ice on Lake Baikal. So what we're hearing here is the impact of the ice cracking. So as it cracks, that boom travels through the ice and the higher frequencies are heard first, and over a long distance this becomes a very distorted pinging sound or a pew sound. In summary, these wave packets are composed of many different harmonic frequencies, and it's related to the Fourier transform. In order to create that non-periodic disturbance, we need to have an infinite sum of harmonic waves to create them, if you refer back to how we constructed a top hat function from a Fourier transform. When we look in non-dispersive media, all the frequencies move at the same phase velocity, which is the group velocity Vg. In the dispersive medium, however, the phase velocities of each frequency becomes different, and the wave packet spreads out over distance. And fundamentally, those effects are observed in light and sound in our everyday experience. So whether we see light refracting into a rainbow, or we hear sound pinging through a railway, or in the video that we've just shown. and we'll revisit this phenomenon as we go through our course.